Imagine looking at China's coastline, thousands of islands separated by open water. For centuries, the sea was a barrier. Then engineers began building bridges across it. Not one bridge, but enormous networks of bridges, viaducts, and tunnels connecting islands to islands, and islands to the mainland. Some routes stretch for dozens of kilometers. But building across the ocean creates problems that don't exist on ordinary roads. Deep water, strong currents, typhoons, shipping lanes, and foundations that have to survive the sea for decades. So how did China build roads where there was almost no land? China's coastal megaprojects combine bridges, artificial islands, tunnels, and massive transport networks. The goal isn't simply to cross one stretch of water. It's to connect entire regions. That means engineers must solve several problems at once. How to support a road in deep water, how to protect foundations from waves and currents, and how to keep ships moving safely beneath the route. The most difficult part starts below the surface. For an island community, geography can be both an advantage and a problem. The sea provides access to ports and trade routes, but it can also isolate people from major cities. Without a fixed connection, transportation depends on ferries, boats, or aircraft. That creates limitations. Travel times can change with weather. Cargo movement becomes more complicated, and large-scale economic activity becomes harder to connect with the mainland. A bridge changes that equation. Once a permanent road connection exists, vehicles can move continuously without waiting for a ferry. Goods can travel directly between ports, industrial zones, cities, and islands. Emergency services can also reach communities faster. But connecting islands isn't as simple as drawing a straight line across the map. The route has to consider water depth, seabed conditions, shipping lanes, wind, waves, and the position of existing islands. In some locations, engineers can build a bridge directly between land masses. In others, the water is too deep or the conditions are too difficult for a continuous bridge. That's when the route becomes a combination of different structures. A bridge may rise over one section. An artificial island may support another. A tunnel may carry traffic beneath a busy shipping channel. And elevated viaducts can connect the separate sections together. The result is not one giant structure. It's a carefully planned transportation system. But the biggest challenge remains underneath the water. A bridge needs foundations. And engineers can't simply place ordinary foundations on the ocean floor and expect them to survive decades of waves, currents, and heavy traffic. They have to reach stable ground. And that can mean working in extremely difficult underwater conditions. A bridge tower can weigh thousands of tons. All of that weight eventually has to reach the seabed. So the foundation becomes one of the most important parts of an offshore bridge. Engineers first study the seabed using geological surveys. They need to know where the stronger layers of rock or soil are located. They also have to understand how currents and waves interact with the seabed. Once the conditions are understood, specialized equipment can install massive piles deep into the ground. These piles transfer loads from the bridge structure downward. Instead of relying on the soft upper seabed, the foundation reaches deeper, more stable layers. But underwater construction creates another problem. The ocean is constantly moving. Currents can make positioning equipment difficult. Waves can interrupt operations. And construction vessels have to work around commercial shipping. In some projects, engineers use large prefabricated components. Sections can be manufactured on land, transported to the construction zone, and installed with heavy lifting equipment. This reduces the amount of complex work that has to happen directly over the water. But foundations also have to survive something much more dangerous than ordinary waves. Scouring. Fast-moving water can remove soil around a foundation. If enough material disappears, the exposed foundation can become weaker. So engineers use protective rock layers and other systems to reduce the effects of water movement. Every foundation is therefore designed not only to carry the bridge, but also to survive the ocean attacking it from every direction. And once the foundations are secure, engineers still have to place enormous bridge structures above them. That is where the real offshore construction begins. Once the foundations are ready, engineers face another enormous challenge. How do you build a bridge deck in the middle of the ocean? The answer is usually a combination of prefabrication and heavy marine construction. Large structural components can be manufactured on land, where engineers have better control over quality and assembly. Then specialized vessels transport those components to the construction site. Massive cranes can lift sections into position and connect them to the supporting structures. This approach reduces the amount of complicated construction that has to happen directly above the water. But offshore bridges have to be designed differently from ordinary bridges. The structure is constantly exposed to wind and waves. Typhoons can generate extremely powerful conditions, and the bridge may cross active shipping routes where large vessels pass underneath. That means the height and position of the bridge have to be carefully calculated. Navigation channels need enough clearance for ships. At the same time, the bridge deck has to remain stable under strong winds. Engineers therefore study how the entire structure responds to aerodynamic forces. A long bridge can behave almost like a giant wing. If wind interacts with the deck at the wrong frequency, dangerous oscillations can develop. So the shape of the deck matters. The stiffness matters, and the way different components connect matters. In some locations, engineers also use long suspension or cable-stayed spans to cross wide navigation channels. These systems allow engineers to create large openings beneath the bridge without placing support columns directly in the shipping route. The result is a structure that looks simple from a distance, but is actually a carefully controlled system of forces. And there is another challenge. A bridge connecting islands cannot always remain above the water. Sometimes the safest route goes under it. A bridge works extremely well when the water isn't too deep and the shipping requirements are manageable. But some waterways are simply too busy for a bridge to cross directly. Major shipping lanes may require enormous clearance. Building a bridge high enough for the largest vessels can become extremely expensive. So engineers sometimes take the road underground. An underwater tunnel can allow ships to pass above without interruption. But constructing a tunnel beneath the sea creates a completely different engineering problem. The structure must remain watertight. It has to resist the pressure of the surrounding water, and it must connect precisely with the roads and bridges on both sides. One approach is to use immersed tunnel sections. Large tunnel segments can be manufactured in controlled conditions, transported to the construction area, and carefully lowered into a prepared trench beneath the seabed. The sections are then connected and sealed. Once the tunnel is in position, protective material can be placed around it. This creates a continuous underground route while leaving the waterway above open to ships. The tunnel and bridge can therefore become parts of the same transportation system. Traffic can move across elevated sections, descend into an underwater tunnel, then rise again onto another bridge. From a driver's perspective, it may feel like one continuous highway. But underneath, engineers are switching between completely different construction technologies. That flexibility is important when connecting islands. The route has to adapt to the environment instead of forcing the environment to fit one type of structure. And once bridges, tunnels, and artificial islands are combined, the project becomes something much larger than a bridge. It becomes a transportation network built directly into the sea. Building a bridge across the sea is one challenge. Keeping it there for decades is another. Offshore bridges face a constant combination of forces. Wind pushes against the deck. Waves attack the foundations. Salt water creates a serious corrosion risk. And typhoons can suddenly turn a calm sea into an extremely aggressive environment. So engineers have to design every major component for long-term exposure. Steel structures receive protective coatings and corrosion control systems. Concrete elements are designed to protect their internal reinforcement from seawater. Foundations are also protected against erosion around the seabed. But the bridge has to move. Temperature causes the deck to expand and contract. Wind creates vibration. Heavy vehicles produce repeated loading. And during extreme weather, the entire structure can experience much larger movements. Engineers therefore use expansion joints, bearings, and carefully designed connections that allow controlled movement. This prevents forces from becoming concentrated in one location. The bridge also needs monitoring. Sensors can track movement, vibration, temperature, and structural conditions. Inspection teams can then identify problems before they become serious. This is especially important for megabridges because their size makes traditional inspection more difficult. A small crack or damaged component might be far from land and difficult to reach. So maintenance becomes part of the engineering strategy from the beginning. The objective isn't to build a bridge that never changes. It's to build one that can change safely and remain functional. And once thousands of vehicles begin using these connections every day, another question appears. What happens to the communities on the islands? Because the purpose of connecting islands isn't simply to create impressive structures. It's to change how people and economies move. A bridge can completely change the geography of a region. An island that once depended on ferries can suddenly become connected to highways and mainland transport networks. Travel becomes more predictable. Cargo can move continuously. Factories gain easier access to suppliers and customers. Tourism can become easier. And emergency services can reach communities without waiting for a boat. But the real transformation happens when multiple connections work together. One bridge may connect an island to another. A second bridge can connect that island to the mainland. A tunnel can carry traffic beneath a major shipping route. And highways can link the entire system to cities far beyond the coastline. What looks like separate megaprojects can therefore function as one enormous transportation network. This is why China's coastal bridge projects are more than individual engineering records. They are designed to overcome geography. The sea creates separation. Infrastructure removes part of that separation. But building the connection is only the beginning. Every bridge requires inspection. Every tunnel needs ventilation and safety systems. Every foundation needs protection. And every route has to remain reliable during storms and heavy traffic. The larger the network becomes, the more important maintenance becomes. Because a transportation system isn't successful simply because engineers finish construction. It is successful when millions of people can depend on it every day. And that is the real purpose behind connecting islands. The goal isn't to conquer the ocean. It's to make the ocean no longer decide where people can go. For centuries, islands were separated by water. Ferries connected them. Ships carried their goods. And the sea controlled the journey. Then engineers began changing the equation. They built foundations on the seabed, raised highways above the waves, created artificial islands, and pushed roads beneath the ocean. Bridge by bridge, tunnel by tunnel, entire coastal regions became connected. The remarkable part isn't any single structure. It's the system created when all of them work together. The ocean is still there. The islands are still separated by water. But now, a road can cross the distance. That is what megaproject engineering does. It doesn't move the islands. It changes the meaning of distance.